Alright, now it's time to talk about atoms, ions, and isotopes. So this would be a great time to pull out your periodic table and have it in front of you because we're going to put it to good use during this lecture. Before we get too far, let's refresh ourselves on what we know about the current atomic model. So to start off, in the center of the atom, there is a densely packed region called the nucleus. And inside the nucleus, you are going to find your protons and your neutrons. Outside of the nucleus is a region that is mostly empty space, and inside of that region, mostly empty space, you're going to find the electrons. And the electrons have a negative charge. So let's talk about each of those particles a little bit more in depth. So what we have are protons, neutrons, and electrons. We symbolize protons with a positive sign because they have a positive charge. Neutrons we symbolize with a little dot because they are neutral, they have no charge. And then there are electrons. And electrons we can symbol with a negative sign, or sometimes you'll see me write them as E negative. Either one of those would work. I like the E negative just because it looks more like an electron. If I just draw a little line like that, sometimes it's hard to tell if it's just a scribble on the page or if it's an electron. So the protons and the neutrons are where the mass comes from in an atom, and they have essentially the same mass. And it's a fairly high mass as far as atoms go. However, the electron has essentially, for all intents and purposes, no mass. Now, truth be told, it does have a mass. We saw the paddle wheel inside the cathode ray, how it spun it. If there was no mass, it wouldn't be able to spin it. But the mass of an electron is 2,000 times smaller than the mass of a proton. What that means is it would take 2,000 electrons to equal the mass of a single proton or neutron. So really, the few electrons that an atom's going to have aren't going to make a difference to the mass overall. So as far as we're concerned, when we look at the electrons, they have no mass in the atom. Think of it like if you had $2 billion and someone gave you a penny, how much money would you tell folks you have? Would you walk around saying, I have $2 billion and 1 penny? No, you would just say, I've got $2 billion because the penny is so insignificant. Electrons are like that. They're just insignificant. They don't matter for the mass at all. So when we talk about the weight of an atom or the mass of an atom, we're referring solely to the protons and neutrons. So here's a nice pretty version of the periodic table. It's got colors and all that kind of stuff. What the periodic table shows us is the most common form of an atom for a particular element. So beyond the periodic table, there's also ions, isotopes, molecules. We'll talk about all those in detail later on. The periodic table itself is arranged by atomic number. So if we zoom in on the periodic table and look at maybe one or two of those boxes, we can look at carbon. Look on your carbon because it'll be easier to read. You'll see this number right up here. That's the atomic number. And what you're going to notice is that number always increases by 1 as we go from one element to the other. So boron is 5, carbon 6, nitrogen is 7, 8, 9, 10, and that goes all the way through the entire periodic table. Atomic numbers always increasing by 1. You'll see other numbers on your periodic table, so the atomic mass, which is down there, and those, they typically increase, but they don't always increase by the same amount, and sometimes it actually goes down. If you look at tellurium and iodine, you'll see that this one goes from 127.6, and that one's at 126.9, so it actually shrinks as you go from left to right on sometimes. So then the best way to think about the periodic table's organization is just increasing atomic number. So let's talk about the atomic number. The atomic number shows us the number of protons that are inside of the nucleus. Now remember Rutherford's model of the atom. We've got the nucleus in the center with the protons and the neutrons. The protons that are in there, we can get the number of them by looking at the atomic number for a particular element. Also, if the atom is neutral, that means it has no charge written on it, it also shows us the number of electrons. Let's take carbon, for example. So carbon, if we look on its periodic table square, you'd see a C, you're going to see a 6 up there, and a 12.0107 on the bottom. So that number on top is the atomic number. You'll always recognize the atomic number because it's typically a whole number on a periodic table. The mass number usually has decimals behind it. The atomic number is always whole, though. It's also always the smaller of the two numbers, so sometimes on a periodic table this would be rounded to just 12, so you wouldn't be able to tell just based on the whole number thing. The atomic number is always the smaller of the two numbers. What this tells us about the carbon atom then is that inside of its nucleus there is going to be 6 protons. It also tells us, as long as the carbon atom is neutral, that out in the electron cloud there's going to be 6 electrons. And we'll talk here in a bit about the organization of those electrons out in the electron cloud, but in a neutral atom you look at the atomic number that tells us how many protons, how many electrons. This is actually the most important number for identifying an element. The number of protons is what distinguishes all atoms from each other. What makes carbon carbon is the fact that it has 6 protons. You can change its number of electrons, you can change its number of neutrons. What makes carbon itself is its 6 protons. If we were to give it one more proton, look on your periodic table. What happens if we go from 6 to 7? It becomes nitrogen. If we take away 1, so it goes from 6 to 5, it becomes boron. The number of protons identifies an element. All right, now let's talk about the atomic mass, or the mass number. You're sometimes going to see it called. So the mass number is always the bigger of the two. For this one, let's look at copper. Copper has the atomic number of 29 and the mass of 63.546. The units on atomic mass are AMUs, and that stands for atomic mass unit. So just a reminder, inside the nucleus there are protons, neutrons, and electrons. The mass, the atomic mass, the AMUs in this case, come solely from the protons and the neutrons. Remember, electrons, extremely small, insignificant for the mass. So what that means is this mass right here, 63.546, shows us the number of protons and neutrons. So each proton and each neutron has the mass of essentially 1 AMU apiece. So then if we're looking at copper here, copper has 29 protons. Mr. Jones, how did you know that it had 29 protons? Because its atomic number is 29. Let's get that mass up to a whole number, just to make things easier. So instead of saying 63.546, which is an average atomic mass, a whole nother story, let's call it 64. That 5 will round that 3 up to 64. So let's think about this. If the mass is made up of protons and neutrons, if each proton is 1 AMU, that means our 29 protons is really the same thing as saying 29 AMUs. So if there's 29 AMUs from the protons and there's 64 AMUs total, we should be able to figure out the number of neutrons because it'll be the leftover AMUs. So 29 from the protons. In order to equal 64, that means we're going to have 35 neutrons, because 29 plus 35 equals 64. And each neutron is also AMUs. So then what we can learn from this then is the number of protons plus, I'm going to circle that proton just so it doesn't look like a plus sign, plus the number of neutrons, I'll also circle that guy, equals the atomic mass. So if we add the number of protons to the number of neutrons, we get the atomic mass. Or, as we're more commonly going to have to do, the atomic mass minus the protons would equal the number of neutrons. And just always remember to round, and same rounding rules as you do in math. If it's 5 or above, you bring the number up. If it's 4 or lower, you just keep it the same. The periodic table is a powerful, powerful tool. You've learned things about it. In fact, this right here is probably familiar from freshman science. There is so many other things that we can do with the periodic table. We are just scratching the surface of the different things that the periodic table tells us about atoms. So the three types of particles, protons, neutrons, and electrons. Let's talk about what happens if we change those. So if the number of neutrons change, we get what's called an isotope. So neutrons, they're neutral. It doesn't change the properties of the element so much. It just changes the mass, because that's what neutrons do. They just add weight. So you can have things like carbon-12 and carbon-14. So the difference between those two is just the mass. So carbon-12 would have a mass of 12 AMUs. Carbon-14 would have a mass of 14 AMUs. Both of them are still going to have 6 protons, because that's what distinguishes carbon from the other elements, is the fact that it has 6 protons. But carbon-12 is going to have 6 neutrons, and carbon-14 would have 8 neutrons. And so it just changes the mass. It's still carbon, still behaves the same, just weighs slightly more. This is why the elements on the periodic table have atomic masses that are long numbers with decimals and stuff, because the number on there is the average atomic mass of all of the different isotopes in the world. And so when you average them out, you don't get nice, pretty whole numbers. You end up with decimals. Okay, if we change the number of electrons, we don't change the identity of the element. We do change how it behaves, though, by making it into an ion. So a change in the charge of an element due to the imbalance of electrons causes it to become what's called an ion. For example, sodium. So sodium normally has 11 protons and 11 electrons. If it loses one of those electrons, bye-bye, and now it has 10 electrons. Well, if we've got 11 positive and 10 negative, those don't cancel each other out anymore. Now we are left with more positives than negatives, and that's going to make sodium Na+. So it's still sodium. It's going to behave differently because now it's an ion, and it's due to that imbalance of charges. Now, here comes a mistake that students love to make. They look at something like sulfur. So sulfur has 16 protons and 16 electrons. And they say, hey, if I add another proton onto sulfur, I will now have 17 protons, and it's going to become sulfur plus. No! If you change the number of protons, you change the identity of the element. It will no longer be sulfur if you add another proton. It will become chlorine, because chlorine has 17 protons. You cannot change the number of protons without changing the element. It's just a fact of life, bada bing, bada boom. You can change the neutrons, you can change the electrons, but you cannot change the protons. And now, ladies and gentlemen, introducing the moment you've all been waiting for, the Bohr model. The Bohr model looks familiar. It's similar to the atomic model that we've drawn so far. We've got the nucleus in the middle, but now instead of having the electron cloud as just kind of a mass out here, we have the electrons occupying these rings that we call energy levels. And we symbolize the energy level with a lowercase n. So what that means is this first energy level, the one closest to the nucleus, is n equals 1. This is n equals 2. And this one's n equals 3. And it can keep going on and on and on, so n equals 4, 5, 6. Each one is just a ring slightly larger than the last, going out from the nucleus. So the nucleus stays the same, it's just made up of protons and neutrons. What's different is the way we draw the electrons out here. Now, what I want you guys to do, and this may be something you're stuck with from freshman science, do not refer to these as either rings or orbits. Both of those are no-nos. That's like saying beef at a vegetarian conference. You do not talk about rings and orbits because they are neither rings nor orbits. They are energy levels. They refer solely to the distance of the electron from the nucleus. So it's just a measurement of radius almost. Electrons do not orbit around the nucleus. They are not just out here spinning in these circles. We just draw those circles to mark a radius of the distance from the electrons to the nucleus. It would be like if you told me, here's the school, and you live 2 miles from the school. So that means you would live somewhere out in this area. And so I could draw a circle saying, all right, so he lives 2 miles, so here's the radius, it's 2 miles. You would live somewhere within that radius. It wouldn't mean that you just sit here and walk around in circles 2 miles from the school. No, you're just somewhere in that area. Same thing with electrons. They do not spin around, they just in somewhere in this energy level. And just for kicks, I'm going to go ahead and spell nucleus correctly. Now, what you're going to notice is each energy level, as we go out, gets slightly bigger and bigger. And n equals 4 would be even bigger, n equals 5 would be even bigger, just because the circles get larger. What that means then is that each energy level will be able to hold more electrons than the last. So if we look at these different energy levels, the first energy level, so n equals 1, has a maximum capacity of 2 electrons. N equals 2 has a maximum capacity of 8 electrons. N equals 3 has a maximum capacity of 18 electrons. And then n equals 4 has a maximum capacity of 32. The way that you remember, the maximum capacity is equal to 2 times whatever n it is squared. And that gives us the capacity of that particular energy level. So for example, this first guy right here, that would be 2 times 1 squared, which equals 2. For the fourth energy level, it would be 2 times 4 squared, and 4 squared would be 16. Remember order of operations, 16 times 2 would be 32. Based on that, n equals 5, what would be the maximum capacity of n equals 5? Well, if we've got 2 times 5 squared is 25 times 2, that means the maximum capacity would be 50. What this means is when we draw out the Bohr model, we can only put electrons up to the capacity. So we always start at the first energy level, so we always start at n equals 1, fill it up. Once it's filled, then we move on to the second energy level and start adding its electrons. Once that one's filled with 8, then we would move to this one. Once it's filled with 18, we would move up to the next one. And by doing this, we can draw a more representative model of the atom. So let's practice by doing this with magnesium. So before we begin, we need to figure out how many protons, neutrons, and electrons there are in magnesium. This should be something that you're able to do, so go ahead and pause the video, look on your periodic table, and figure out how many protons, neutrons, and electrons there are in magnesium. Alright, hopefully you got 12s right across the board. Nice and easy, 12 protons, 12 neutrons, 12 electrons. So let's take those and put those into a Bohr model then. First thing we want to do is draw our nucleus. And inside the nucleus, we don't need to draw 12 protons and 12 neutrons. Instead, we can just write in there 12 plus to represent 12 protons and 12 dots to represent 12 neutrons. Next comes the electrons. So let's start by adding our first energy level, so n equals 1. So we've got 12 electrons to disperse. The first energy level can hold 2, and these we want to actually draw out. So let's draw 1 electron and 2 electrons. Now the first energy level is filled to capacity, so we can't put any more there. We can't put all 12 there. We can't even put 3 or 4 there. Once that's filled, we need to go to the next one. So let's draw n equals 2, the second energy level. Now the maximum capacity of that one is 8, so we can go like this. We now have 3 electrons out there, 4, 5, 6, 7, 8, 9, 10, and we have filled up the second energy level, and we've only used 10 of our 12 electrons. So we have 2 in the first energy level, we have 8 in the second energy level. Looks like we're going to have to add a third energy level. Now, not all atoms have all energy levels. We just write them when we need them. So we can go ahead and start filling this one. We're going to put 1 and then 2. Now at this point, we're done with the electrons. We don't need to fill up that third energy level. We have 2 in the first row, 8 in the second, 2 in the last. That means we have 2, 10, and 12 electrons, just like magnesium should. Pretty simple and probably familiar from freshman science. Something else that we need to know is these outer row electrons. The outer electrons have a special name, and that is valence electrons. Valence electrons are significant because they tell us a lot about the element. They're the ones that distinguish all of the bonding, all of the reacting. Really, a lot of the properties of an element are due to its valence electrons. The inner electrons, so all of those guys that are in there, are called the core electrons. But really, they're not that significant. They don't really play a role in the bonding or anything like that. It's these outer row electrons, the valence electrons, that really matter. So remember that term, valence electrons, for the outer row electrons, because they're going to be the ones that we talk about a lot during chemistry. And that leads to the last and final way to represent an atom, and that is using the electron dot model. This one might be a little bit more familiar to you. So what that one uses is the atomic symbol, so magnesium is Mg, and then we just draw dots around magnesium to represent the number of valence electrons. So we do nothing with those core electrons, just the outer ones. So magnesium, we can see it has 2. So I usually start in the top and then we just work around clockwise. So it'd be Mg with 2 electrons on it. Sodium that we looked at earlier that has 1 valence electron, we would just draw 1 dot. And then a noble gas like neon that has 8 valence electrons, we would draw 8 dots around it. Okay, and you always draw them in pairs, no more than 2 per side. Alright, that's it. So those are all the different models of the atom. Hopefully by now we'll be able to draw some in class.